Hey, everybody, and welcome to Chapter 11, Liquids, Solids, and Intermolecular Forces. Now, remember where this chapter goes in our textbook, just to kind of remind ourselves where we have been and what the theme of our semester should be. Now, this chapter comes right after chapter 10, which we did last semester, which was on gases. And so gases was our first introduction to that gas phase and seeing all the physical properties that gases can contribute. Liquids and solids in this chapter are similar, but they are different states. We push them together because they are more similar to each other than any other state is to a gas. And so we've just come from understanding thermodynamics. We're now going to integrate the idea of liquids and solids and the intermolecular forces that they hold together so that we can truly understand an overall reaction. We've hinted to some phase changes already in the previous unit, and so we'll see a nice correlation with those together in this chapter. So you might have heard this before, structure dictates function. That is the theme of this chapter right now. We're going to see a lot of physical properties. We're going to see a lot of chemical properties later on, but structure of a molecule determines its overall properties. And it's that chemical composition, which atoms are connected to what other atoms, how are they connected, and what does the overall three-dimensional shape look like, is what is really important to understand intermolecular forces. So we're going to go through a brief review of Lewis structures in class, and we're going to do a little bit about VSEPR theory, which was our three-dimensional shape chapter last semester. If you want to go ahead and do that before coming to class, you totally may. Focus on chapters 4, 5, and 6. Now, intermolecular forces are attractive forces that exist between all molecules. Between two molecules at least, all right? So when we're gonna draw an intermolecular force, we have to be drawing at least two atoms connected via this attractive force, not a chemical bond, okay? An intermolecular force is what holds liquids and solids together. They're actually the responsible nature of why liquids look the way they do. For our biological applications, DNA is held together, the double helix is held together by an intermolecular force. You may have heard about that one, hydrogen bonding. We're going to talk about what that means in terms of the chemistry of molecules. So the phases of matter, solid, liquid, or gas, really depend on the magnitude of the intermolecular forces between the particles. And that is going to have with it a thermal energy responsible to overcome those intermolecular forces. When thermal energy is high, so when we have really, really high temperatures, we've given the state of matter enough energy to overcome the intermolecular force and be a gas. If the thermal energy is low, temperature is low, matter tends to be a liquid or a solid because there's not enough energy to overcome the intermolecular forces. And so the molecules tend to stick together, get closer in proximity, become liquids, or even closer in proximity, become solids. So we'll have this idea, properties in the states of matter. Gases have very, very low densities, right? If we just remember what density is, it's the mass divided by the volume. Gases have very, very low mass, and they take up a lot of space, right? So they would have very, very low densities. What that means for us is that the intermolecular forces are relatively weak. We use the ideal gas law equation in chapter 10 to identify the fact that we understand that most of the time gases act independently. The particles are individualized particles moving around in the space provided. We will talk about liquids and solids though. Their densities are relatively high. They are more compact when we look at the overall structure of the solution or the substance. Now, liquids have an indefinite shape, right? They can conform to whatever shape the bottle is, but they do have a definite volume. The strength of the intermolecular forces for liquids and solids are moderate to strong. Okay, solids are more highly compact, they have a definite shape, and so their intermolecular forces are what's really holding the solid together. We're going to discuss liquids a lot because liquids can make solutions, and so we can change the intermolecular forces of a pure substance when we start to integrate it with another substance. The solute-solvent interaction will be of importance in chapter 13. Solids, liquids, and gases, just another comparison, we can see that of water, the three states of water. Now, water is very, very special because when we look at the intersection between the solid and liquid states of water, we actually see that the solid ice is less dense than water. This doesn't happen often. Most solids have greater densities than their liquids, and why ice solid water has a lower density than liquid water is because of the crystalline structure that it forms. It forms a very open crystalline structure, and that's why we see liquid water at 1 atm has a density of 0.998 grams per centimeter cubed. And once it gets into that solid ice structure, that state has a lower density because of the crystalline structure. All right. Liquids. So let's talk about what the state itself looks like. This is a molecular representation of a liquid where all the molecules are kind of just bouncing around. They are closely packed, but they have some ability to move, okay? And so they have some ability to integrate other molecules in a solution. I'm saying that because in chapter 11, we're going to focus a lot on pure substances. And then when we get into chapter 13, the only added benefit of chapter 13 is let's talk about solutions chemistry now and see what intermolecular forces can become apparent to us. So in a pure substance that's a liquid, we do have close packing where liquids then cannot be compressible like gases. Just as that reminder, gases are compressible, right? They have enough space around them that they can be compressed or expanded, and that will change pressure, right? Change of volume, change of pressure. However, liquids can't do that. They're close enoughly packed together that liquids can not be compressed. However, they're not that closely packed that they can't move around. They do have a ability to take the shape of their container and to flow. And so therefore we do see that solutions are able to form in liquids, right? Liquids are most often the solvent of our solutions. Solids are packed close together and they are in a fixed position. So when we talk about solids, there's an inability of the particles to move around. And so solids retain their shape and the volume, even when they're placed in a new container, even when they're placed from a jar onto a weigh boat or onto the desk. Right? So solids are either one of two organized patterns. They're either a geometric pattern called a crystalline solid, such like water, salts, right? Diamonds are also, those are all crystalline solids. Solids do not need to show that geometric pattern. They can be called amorphous solids. These are like plastic and glass. And so you can see they are less structured, they're less ordered, they're just kind of clumped together. Now, the overall phase changes between the states can occur because of thermal energy, right? You start with a solid and then you add heat, and that heat can make it a liquid, right? So that process of going from a solid to a liquid is an endothermic endothermic reaction. You have to put heat into the solid in order to get it to melt. Same thing as going from a liquid to a gas. If we add heat, we can get a liquid to evaporate. And that evaporation, again, endothermic. Heat has to go into the system. This is why sweating is so great for us. We have a lot of liquids in our bodies and we have sweat glands. And what happens in those sweat glands is our liquid water evaporates out of our body. Endothermic, we end up getting cool, right? Now we can go the other way as well, and we can think that a gas to a liquid transition is exothermic, or a liquid to a solid transition is also exothermic. Heat has to be removed to go backwards. Now we're going to just transition over to a short video that shows the phase changes between liquid nitrogen by changing the pressure, okay? So again, if we change heat, we can talk about exothermic or endothermic, but also listed here is the idea of pressure. If we take a gas and we compress it and we push down and we push and we push and we push, increasing the pressure on it, we can make it become a liquid. If we take a liquid and increase the pressure and pressure and pressure and pressure, typically it becomes a solid, okay? There are some exceptions, specifically with that of water, when we're talking about the density of the solid versus the liquid, but most solids are more dense than their liquid form. So let's take a look at that video just to see a real life example. Now this is going to be liquid nitrogen. Liquid nitrogen is starting off boiling because at atmospheric pressure, nitrogen should be a gas. Okay, so we've reduced the pressure in this sample. And so what we're going to do is play with the pressure and see if we can't convert that liquid nitrogen or convert the gaseous nitrogen back into a liquid, stop it boiling and put it back into a solid, okay, by increasing the pressure.
By cooling it. I'm going to use this vacuum system, and as it evaporates, the heat goes off with the gas, and the liquid that's left behind gets colder and colder. And at some point, we're going to get below the melting temperature of nitrogen, and hopefully we will see solid nitrogen. And I'm going to do this. First, I'm going to turn on the pump. And then quickly. So the nitrogen is boiling now because the pressure over it is lower than its vapor pressure. It's internal heat that's causing it to boil. It boils, it cools, and then what we see is solid nitrogen. Here is dry ice. If we raise the pressure, we can put the dry ice, we can put the carbon dioxide in a place where it can exist as a liquid. Going to seal it up so that the gas cannot escape. Because the gas can't escape, the pressure inside of the tube is going to go up. When the pressure inside of the tube reaches about 5 atmospheres, the dry ice reaches a point where instead of going directly to gas, subliming, it can melt, it can turn from a solid to a liquid. Now what's going on right now is heat going into the tube is causing the dry ice to sublime. As the gas builds up inside of the tube, the pressure goes up. And as the pressure goes up, there it goes, the dry ice now can melt. Now we have mostly liquid. And if I release the pressure, the liquid carbon dioxide can no longer exist as a liquid. And because it's still cold, it condenses straight back into a solid.
All right, so what are intermolecular forces? We've talked now about that they hold this matter together in the condensed state, liquids or solids. And what exactly are they? Well, they are an electrostatic attraction that is existing in nature. And the strength of that electrostatic attraction between particles of a substance is what is going to determine whether the gases or the particles are held far apart. Gases, are they held closer together? Liquids, are they even closer together? Solids. The stronger the attractive forces, physical properties will follow. The higher the boiling point of the liquid, if you have a strong intermolecular forces, you're not going to want to go be a gas. You're not going to want to go be independent. You're going to want to stay where the intermolecular forces of attraction exist. The higher the melting point of the solid will be, again, because solids are closest together. So that's where attractive forces are in higher prevalence. So the stronger the force, the more likely the substance will want to keep those forces. They do vary in strength, weak to strong. So when we're talking about there are 4 main types of intermolecular forces. One is going to be based off of solutions, and so we'll most likely deal with that next chapter. But there are going to be weak forces and strong forces. And so the stronger the force, the more the particles want to stick together. That's the overall theme. Trends in the strength of intermolecular forces. The stronger the attractions between the atoms or the molecules, the more energy it will take to separate them. All right, so 2 particles, think Romeo and Juliet. They have a very, very strong attraction. We need to provide as a surroundings a lot of energy to separate those 2 particles, okay? So boiling a liquid requires energy. It's endothermic, right? And so when we think about the attractions that the liquid molecules have to each other, the IMFs, the intermolecular forces, boiling will overcome those intermolecular forces. Now notice this is not intramolecular, this is not chemical bonding that we're breaking. We are simply changing the state of matter. Okay, so typically what we can see is the higher the normal boiling point, normal just meaning at 1 atm, the higher the normal boiling point of the liquid, it will correlate with the stronger intermolecular forces of attraction. So why are molecules attracted to each other? Well, it's because there are electrons and protons in these molecules, and when we actually exist as molecules, we can have polar charges, right? We can have the delta charges, the partial charges, and those opposites attract, okay? So looking at that of water, we have an oxygen and a hydrogen bond. We know that that is a polar bond. Oxygen is a little bit more negatively charged than hydrogen. Now, these aren't ions, these are polar covalent bonds. And when that happens, the opposites, the oxygen of one molecule with its delta minus can be attracted to the hydrogen of another with its delta plus. And that is the intermolecular force, all right? Bigger distance, right? It's not a covalent bond. The covalent bond between oxygen and hydrogen is around 96 picometers. The intermolecular force, if you were to think about that, is a much greater distance, okay? So when we're looking at these intermolecular forces, they are not chemical bonds. They are electrostatic forces of attraction. Now, even nonpolar molecules will have temporary charges, temporary dipoles. They're instantaneous, they're fleeting. We're going to talk about them. They're the weakest type of intermolecular force. All right. So 3 main types that we're going to talk about in this chapter. First one's called dispersion forces, also called London forces, or sometimes combined London dispersion forces. They are also called van der Waal forces. Every molecule has London dispersion forces. Every molecule will have these temporary dipole moments where there's an unequal electron distribution that leads to attractions, okay, between other molecules. If a molecule has a permanent dipole, if it actually has polarity, remember last semester we were able to draw a Lewis structure, analyze the central atom and say, is this molecule polar, right? Then if there is that permanent polarity, then we can actually have a little bit stronger dipole-dipole attractions. The reason why it's stronger than our van der Waals forces is because these polarity dipoles are already permanent in the molecule, whereas the van der Waals are temporary, all right? When a dipole is especially strong, it's resulting when a hydrogen atom is attached to an extremely electronegative atom. These are called hydrogen bonding. I sometimes abbreviate it H bonding, which is right. I wrote that right there. It has to be a hydrogen with an oxygen, nitrogen, or fluorine. That covalent bond is extremely polar. Now remember, this is a covalent bond. When this bond is present in a molecule, that's when that polarity difference creates an extremely strong permanent dipole. And that interaction between two molecules that have these extremely polar covalent bonds, that is called the hydrogen bonding. All right, weakest of intermolecular forces, dispersion forces. When the fluctuation occurs, it's because of proximity. As we get two molecules to come closer together, think about these two molecules, or even all three of them, getting closer together because they're swarming around in this liquid solution. We're going to pretend that we're in liquids, okay? What happens is an instantaneous dipole. Notice the electrons can shift over to one side, creating that delta minus and the delta plus. And then the electrons of the next molecule can shift over as well, creating a delta minus and the delta plus. And by proximity, these guys are getting closer together just because that's, floating around in the solution. There's the intermolecular force. When the delta plus of one is attracted to the delta minus of the other. There's our IMF. Okay? Now, all molecules have this ability. All molecules have the ability to temporarily distribute their electrons in an uneven way. They're fleeting, they're not very strong, and that's what we would call them, the weakest of the intermolecular forces. Now, size, molecular size, or atom size will have the effect on this dispersion force, okay? So notice this chart. As we increase the molar mass, we're increasing the size of the ability to participate in dispersion forces. This is called polarizability. We have more spaces to distribute those electrons unevenly, right? And therefore, notice the boiling point. Higher molar mass or higher surface area, the higher the intermolecular forces, which result in the higher IMFs, right? And a higher boiling point. Dipole-dipole attractions. Now, these dipole-dipole interactions exist between already established polar molecules, okay? So already we have here acetone. This is a molecule of acetone, which is found in nail polish remover. It's found in paint thinners, things like that. It already has a polar bond. It is already a polar molecule. All right, that carbon to oxygen double bond is polar. Oxygen is more electronegative than carbon, and therefore it exists with a permanent dipole already in one molecule. So what does that mean? the delta minus of one actually will align with the delta plus of the other and create an intermolecular force. There it is with its neighbor, all right? The delta minus of one getting attracted and lined up to the delta plus of the other is the intermolecular force of attraction. We can see that in these electrostatic potential maps. These are really helpful for us. We actually can calculate these and do a lot of mathematical representations to where red areas are areas of high electron density, blue areas are areas of low electron density. So we can think delta minus, delta plus, delta plus, delta minus, all right? Let's talk about hydrogen bonding. Last one. When a very electronegative atom is bonded to hydrogen, it strongly pulls the bonding electrons towards itself. Examples, oxygen, nitrogen, or fluorine. Why it's these three polar covalent bonds that we want to discuss in hydrogen bonding is because hydrogen is very small and it's paired up with a very small, very electronegative atom. These three, oxygen, nitrogen, and fluorine, are some of the most electronegative atoms we have and the smallest size. Because hydrogen has no other electrons, when the electron density is pulled away, the nucleus is really de-shielded. That means that the proton, the hydrogen nucleus, the proton there is very exposed. And so that de-shielding creates a very, very special delta plus to the delta minus, okay? And so that exposed nuclei acts as a very strong center of positive charge. So when we think about HF here, we do have a delta plus and a delta minus, and that will be attracted, and the molecules together in a solution will line up to have the attraction between one delta minus and the other delta plus, all right? And that's an interesting factor with this ability to line up and to organize a bunch of molecules together. We can still see the electrostatic potential maps there. The red side or the orangey side is the delta minus attracting to the purpley blue side, which is the delta plus. All right.